Thank everyone for attending today. Building better with thermal breaks. We think that we have some products here and some strategies and applications that will be of interest to you. Just a quick thing about our products so that you're better oriented during the presentation. We have three basic lines here. FRR, fabric reinforced resin, which is a very strong material, and that is that guy back there, that product 500 series ultra high density polyurethanes right there that I use. There's four different densities, and then Armagert, which is a pultruded fiberglass Z-girt that replaces steel Z-girts. So this is an AIA CES provider, and we are happy to get you your credits and so forth at the end. So, it's always the struggle between form and function, and we are certainly all about function. That's what we do here. We try to improve buildings to make better, more efficient buildings. Because buildings produce about 40% of our carbon footprint, it's our responsibility as builders, designers, architects, engineers, and manufacturers to build better buildings. A lot of our operational emissions, 28% come from heating and cooling, and that's where we're going to talk about improving the envelope with thermal bridging strategies, thermal break strategies. We've known about energy efficiency and how it slows climate change and it does makes people more comfortable and so forth in buildings for a long time, but we're slow to change. We are slow to change. I've been doing this for, God help me, 40 years or so, since the early 80s. And I've seen a lot of changes, and they always come slow and with some slugging. So it's time to change. The AIA is all over this with a climate action plan. You probably have seen that. So let's get right to it. Course overview. Thermal bridging is a common occurrence in mid and high rise commercial office buildings, along with every other building. All kinds of buildings are affected by thermal bridging, and that really pertains to our older designs. And
Mhm.
so when we deal with it, when we don't deal with it, we have a larger carbon footprint, and that'll happen for a long time because of the service life of buildings, 50 to 100 years. Moisture issues related to condensation, where cold spots can create condensation, where you have some building degradation. People are uncomfortable in places if there's thermal bridging or heating omissions and so forth, and supplemental heat is sometimes needed, and higher energy use, operating costs, and the associated carbon footprint. One size does not fit all. Our company does this all over the country. We do seminars and we distribute. And depending on our climate zone, and we're in a pretty cold one here in Massachusetts, we need strategies to address each of those. So, our learning objectives today: understanding what thermal bridging is. And I find there's a very uneven understanding of what it is, how it works. We'll discuss uh, thermal bridging in roof, wall, and floor assemblies, and talk about UR and K values associated with building materials. Examine strategies and application on how we can improve and identify and improve these thermal bridging places, avoid condensation, and then the ASHRAE standards, and LEED V5 is out now. We're all heading in the right direction with that. So our first learning objective: effectively dealing with thermal bridging will improve energy performance of buildings by 30 to 60%, according to Morrison Hershfield. Now, this naturally depends on the design and how much bridging is in the design. And when we do address it, we can lower energy use, make people more comfortable, reduce the potential for condensing surfaces and the associated problems there, and reduce emissions, which is what we're really shooting for, along with everything else, to build a more sustainable future and getting closer to our goals. The high performance buildings, net zero, passive house, and all others are really a lot of it depends on thermal bridging strategies. So, what the heck is thermal bridging? A thermal bridge is a conductive pathway over which heat can flow easily. It is the path of least resistance. Steel and concrete are wonderful building materials, but they're very conductive. And so heat can flow over a steel beam or a concrete wall easily, and it will always travel from warm to cold. That is the second law of thermodynamics. And that is what we are trying to impede or control how much thermal bridging happens. Now, I wish I could tell you we stop thermal bridging. We don't. We mitigate it. We control it. We reduce it in and because some of the building design really lends itself to thermal bridges that really dump a lot of heat out into the environment. A lot of what we've learned comes from the Morrison Hershfield Building Envelope Thermal Bridging Guide. The guide is it was commissioned by BC Hydro, and that's where you'd find it online because Morrison Hershfield has been swallowed up by a large company called Stantec. But that said, there's also a 4-part YouTube series you can look at, which is very informative and instructive on this, and that would be found again under BC Hydro Building Envelope Thermal Bridging Guide. It's really good stuff. So in that guide, they use a lot of 3D computer simulation that can predict how much thermal bridging will occur, where it will occur, and so forth, based on all of the building materials that are used and the way that they're located in the buildings. This is something that you'll see in the bridging guide, and they will call out, say, for instance, a balcony of slab edge connection, and they'll call out from efficient to poor, and until recently, poor could have been code compliant. So we're all hopefully pushing in the same direction to make buildings more efficient based on how much we can reduce thermal bridging. Well, infrared cameras are an instructive and interesting, useful tool when we look at the thermal signature of a building, because it's going to call out the temperature differences as is. Now we've used these for Christ the last 40 years, but they're so accessible now. You can get an app or a little camera that plugs into your phone, and you can create infrared thermal imaging with that. Because we look in the infrared spectrum, we can see where the problems might be, and it's a little difficult after the building is up. So we need to get after it in the design phase. But wherever there's conductive building materials, steel, concrete, aluminum, connected from the conditioned space to from the inside to the outside, thermal bridging occurs. And the greater the delta or the temperature difference, the greater the drive is going to be across that boundary and out into the environment where we dissipate a lot of heat that we don't really want to dissipate. So thermal imaging is a useful tool. So some quick terminology. The insulation boundary in a building is the thermal envelope, the thermal conductivity, the amount of heat energy a material will conduct in BTUs per hour per square foot per inch of thickness in degrees Fahrenheit. That is the measurement that we use. So thermal break is a material with low thermal conductivity and high strength, because these are in transition areas quite often, most often, on the thermal boundary to inhibit energy loss. And now K, R, and U values. K value is the rate of conductive heat flow. R is the resistance to heat flow. And U is the assembled wall, roof, or floor. That's what really counts, is the assembled area. So when we ignore thermal bridging, we're not going to produce the accurate picture of what our insulation is supposed to be doing. In this chart, the blue bars that you see are, the bars that you see are usage, or the amount of energy used. So we want low bars here. So what we have is on the blue bars, you can see, let me get going here with my little thingy majig. Uh, you can see here with uh, no exterior insulation and to the left and R25 to the right, you can see that in this particular wall setup, the metal Z-girts are reducing the effectiveness of the insulation. Even though we have R25, it's acting more like R5, and that's not good. So when we put the same insulation, the R25, on a more effective, more less conductive Z-girt in this case, you're going to get much better results. You're going to get R16, which is going to insulate a whole lot better. So that just a look at that. And we know we've been using steel Z-girts for a long time to hold the insulation, continuous insulation outside. We can do much better when we use non-conductive Z-girts like these FRP pultruded fiberglass Z-girts, which are plenty strong, and they are much less conductive, so that you're going to get much closer to the R value that you're calling out. So U value is important because it's not what's on the bag; it's what's on the wall and how it performs in that situation. You can see here that R19 insulation probably doesn't act like R19 because of the because of the bypasses that are created in the mounting system. So what what I like to say is it's not what's on the bag, it's what's on the wall. That's why we've gone exterior continuous insulation. You can see here that even though you have cavity insulation, there are it doesn't really stop until we get to the exterior wall and the where you have continuous insulation outside that is going to do a much better job than even the cavity insulation at a much thicker. So, a quick word on sequencing. Sequencing is a word that all high performance planners and architects look for. And sequencing is important because traditionally some of these trades up on the building can take apart the WRB, or the insulation can be not continuous, and we need to help out this guy in the field, this guy here, who is setting up the sequencing, the different trades that come through. And it's very important that the supervisor in the field have plans that are clear and easy to follow and detailed, because if your HVAC guy comes along and maybe tears up the insulation layer or the vapor barrier or so forth, that's not good. But what we're really dealing with is continuous insulation, and continuous insulation uh, is something that really often happens where thermal bridging uh, occurs. So let's look at some of those things. So K value of common building materials. Copper, you probably would have predicted, is very conductive, and it is. But what we're really interested in is this mild steel. Mild steel is what this building on the right is built from, and what every prefabricated steel building is built from mild steel. So it is conductive, and it is wonderful. It's fast, it's strong, but it also has some problems with insulation, because wherever it's connected from inside to outside, that steel flows. Heat will flow along the steel beams and out into the environment. And so you can see below here, the insulating materials have very low conductivity, and that's why we use them for insulation: polyurethane, rock wool, cotton wool, and those type of things. But this building just happens to be a cannabis factory here in Massachusetts, And what's interesting here is it's pretty susceptible to thermal bridging because the beam that you see sticking out, it's kind of hard to see with this color, but the beam that you're sticking out is can be problematic. I call it this is my poster child for thermal bridging. This is the same picture, the same building, and a different look because the thermal bridging happens where those steel beams are attached to the steel substructure, and it's a highway. It's a highway for heat loss because there's nothing stopping that beam from just sticking out in the environment and dissipating heat. So a simple fix here would have been simply a thermal break that goes in and separates that steel rafter, we'll call it. There's dozens of these, by the way, that go around this building, dozens, and they're attached right back to the steel. And it's a missed opportunity because a this is not a very difficult structural load here. You can see here's the finished building. You can see that there's legs under these rafters to hold up that. So snow loads and wind loads and so forth aren't as big a factor. But it's again, it's a missed opportunity in a place where the thermal breaks could have done a great job. But anyway, live and learn. We move on. Some more terminology. Everyone loves terminology, right? Uh, Clearfield transmittance. A lot of these came from the development of thermal bridging and some of the vernacular that came from that. Clearfield transmittance is the heat flow through the wall, roof, or floor assembly, and that's heat flow per area. But we add into that when we look at thermal bridging, linear transmittance, or psi in engineering terms, it's the additional heat flow caused by exposure due to length. And those are areas like slab edges, parapets, corners, brick shelf angles, cladding, and insulation retention girts. And the chi value of point transmittance is the additional heat flow caused by points that may include bolted on canopies, balconies, windscreens, signage. This happens in almost every building. So we need to look at that more closely. And you can see that we'll call our last picture there, the cannabis factory, a canopy type of situation where it's bolted on and it creates some connection from inside to out, which is the thermal bridge. So Clearfield transmittance, or the U value, is an assembled wall, floor, or roof. You can see in this picture that the steel studs are really radiating a tremendous amount of heat through the wall. And, these are, you can't hide from the thermal camera. The temperature difference is showing here. It's connected the inside of that stud to the outside wall. This probably doesn't have any exterior insulation, so it's kind of it's a big thermal bridge, and this is why we've gone outside, continuous insulation outside. It's cavity insulation, but and that's the Clearfield. Linear transmittance is the linear thermal bridges that wrap around the entire building, and they are, just as I said, cladding, retainers, shelf angles, slab edges, balcony, those kind of things. And they comprise a large part of the thermal footprint. And then point transmittance, just like the cannabis factory, we saw they're bolted on back to the frame. Only in this case, we have a thermal break that just gives you separation and uh, improves that connection quite a bit when it comes to thermal bridging. But again, these are the areas, the chi value of the point transmittances. There could be a couple of dozen of these, and there could be several hundred. So we got to inventory and find those. So what happens here, what's really spawned this whole conversation about thermal bridging is when we're looking for the total heat flow per area, we have to add in linear transmittance, point transmittance, along with the clear field, which is the only thing we used to consider. And then in this mathematical equation, we come up with a much better picture of the overall load, thermal load, and heating and cooling loads of the building. So in the design phase, we need to round up the usual suspects, and those are areas where thermal bridging commonly has occurred in traditional design. And those are balconies, structural columns and footings, foundations, wall assemblies, and so on. But the biggies are, brick shelf angles, parapets, and we'll get into that a little bit more as we roll along here. But let's talk about balconies. Balconies can give up a lot of heat, and this is kind of all over North America, we're chasing how we make balconies more efficient. I want to just call your attention to this heat sink to the left, which is designed to dissipate heat. And they do that by creating a lot of surface area outside on these plates. And then they blow air up through it in order to get these plates to create the surface area and dissipate heat out into the environment, whatever it is. This might be in your computer, refrigerator, or even actually the radiator in the front of your car. So that's how we transfer heat. But balconies unintentionally do the same thing by connecting the heated space to the unheated space outside. And balconies can really create a lot of surface area that create a thermal bridge and dissipate heat unintentionally across that bridge and outside. We can interrupt it. It hasn't been done in traditional design, but now the building industry is calling for thermal breaks right along the thermal boundary, which would be the patio door or the exterior wall. And that thermal break would slow down. Once again, we're not stopping thermal bridging, but we're reducing it to a manageable amount. Slow it down so that we aren't losing so much heat across that space. And the thermal break positioned properly and engineered properly can do that. And so let's get on to the next slide here. And that shows you this is an example of a thermal break in that connection. Now, this is our version, and we have been developing this for several years. And the forces here that we're dealing with are their intention on top. The rebar does all of the heavy lifting. The rebar is the building component that holds the building together. Concrete by itself isn't that useful. So on top we have tension. On bottom we have compression. Those are the forces in play here. And in compression, in our system, we have concrete cylinders that will offset that compressive load on the bottom, and shear bars actually to take care of the shear forces that happen going through this way and out that way. So anyway, this is the way we're attacking this challenge, and it's been engineered and it's working fine. Once again, this is doable. This is on the market and we're able to approach it. We know it works. It's been working for quite a long time for high performance builders, especially in Europe, by the way, where this has been identified as a problem and have been working thermal bridging in balconies for quite a long time. So that's poured in place balcony thermal break. It also works in steel connections where, say, for instance, this member here is sticking out from this beam is sticking off of the building. I guess someday back in here is going to be the heated side, and then this beam is sequestered or insulated or separated from the main part just like the missed opportunity we saw there back at the cannabis factory. So, you know, there is design that is needed to be changed. We can't just run beams through the building and expect that to work out in our favor, thermally anyway. Because what we used to do is in this middle piece here, we would say, okay, we have an element here, we have a detail, it's a canopy, it's a balcony, it's a whatever it is, and we used to say to our steel fabricator, just go ahead and make that steel beam that's going to run straight through the building, and it's very strong that way. But we've come to the realization that um, this is a heat highway, and unimpeded heat can just run across the beam and out into the environment, and uh, and that's a huge heat loss because it flows through there every day, every night, all year round. So what we need to do is we need to interrupt that with a thermal break in this steel beam situation here, right on the thermal boundary. It's got to be on the exterior wall. It's got to line up. And where we had a steel beam running through, now we're asking that the fabricator cut and plate, and we bolt it back together with a thermal break in the middle, which is going to give you some insulation and stop the flow, reduce the flow to a manageable level from inside the envelope till out. So engineering wise, whether it's a shear moment connection, whether you're calculating snow loads, wind loads, whatever it is, the engineer on site has to be comfortable with it. He has to assign whatever safety factor he is going to make him able to sleep at night. So that is because there's so many different details. There's so many different uh, situations that the engineer on site has to sign off, and we can all move on with a more efficient building. So we have been insulating like the floor of cold storage buildings for a long time, and prior to that, they used to use wood in there because thermal buildings, freezer buildings, and food storage and so forth have been pretty serious about thermal bridging for quite a long time. You can see in this situation, this thermal break is able to carry the load and line up with the insulation that's going to be installed in the floor, and get you the continuity under those beams, so that in this case the heat isn't coming up from the ground and in in creating a problem at the bottom of these beams. More on that shortly. Also true of the transition from the roof through the insulation and up, maybe for legs of uh, air handlers or signs, windscreens, whatever it is that's penetrating up on the roof. We have to look at that carefully and say, how can we insulate or separate these steel elements from the whatever they're connected to down below, because it's structural, and line it up, and it really should be lined up with the insulation layer on the roof. So moving on, I mentioned that we have done structural columns and piers and so forth for a long time. In cold storage facilities like this one, you can see this is leveled up, shimmed. You can see the shims in there, and then it will be grouted, and that is going to give you exactly what you need for to get the separation and have the structural loading on that column. This is just what it would look like on the plan, where it's in line with the floor insulation. And it's also true, this is a passive house in Pennsylvania where this is not a cold storage, and this one has been grouted, and this one is ready to move, ready to get their floor insulation and concrete. Here is a this is a pad, structural pad, 5 inches thick. Uh, Here on you can see let me just run you through the process. Uh, we'll get a call and they'll say, okay, we need a pad that is 48 by 18, 5 inches thick. You can see the five right there. We'll cut it and bond it together and everything. They'll give us the location of the dowels or threaded rod or whatever it is they're using. We'll cut it. It shows up on site ready to drop on those beams, drop on and then the foot of that column is going to go right on top of it. It's going to be bolted down, and then it's going to be in in plane with the any floor insulation that they have going in there. But these in these weight bearing areas, this is just fine, and we do these all the time. It's another example. You get the idea. And again, very important for these folks to get it right. But because it's down on grade or below grade, the drainage, the the drainage, weatherproof, damp proofing, and water barriers, and all have to work together to get to the right thing, the right the right kind of detail. Here's a here's a the actually Framingham State University, where this is a continuous block stacked right on top of a, a thermal break, a weight bearing thermal break detail, so that they have continuous insulation out of the ground and then across the floor. And that is that's a detail that we're seeing more and more often to get the continuity and to separate that wall from the cold ground. Here's a passive house, and this is in this case we're looking for complete separation here because this is an unheated garage, and I can tell you through my career how many times we've seen unheated garages creating very cold first floors. But in this case, it's totally separated with a plate that goes under that exterior weight bearing wall and continuously all around this building in a way that is going to work with the wall insulation, connect it all so that we have continuity and well fitting uh, detail all the way around. Brick shelf angles are another uh, area where we see uh, bolted on bolted on steel, galvanized steel, separated with a structural thermal break that's able to carry that load and give the appropriate uh, bearing and creating a space behind it for your ISO or rock wool or whatever it is. We've talked about walls a little bit, but they're really taking it seriously now. The attachments need to be thermally broken because the picture on the right is a steel Ziegert holding those on, and those stripes are heat loss. And we talked about it briefly, but steel was great in its day, but now we can switch to for instance, a system like this FRP system, Ziegert, that does all the same things, and your installer knows how to put them on. So there's no difference in the installation methods, and we know this works. I know a lot of you folks are from Massachusetts. This is right down looking over Polar Park in Worcester, and you have continuous insulation that is a rain screen type of situation with the furring right there in the middle, with the furring holding off the siding so that you have the space for drainage and drying. It's just a look at what it might look like on the plan. Let's move on to parapets. Parapets are a spot that's of high interest because it's a very weak area of insulation if it's not dealt with in the design. There's so many different ways to build a parapet. This one is completely poured. This is a poured concrete roof deck and a poured concrete parapet. in the first case to the left, you have a serious thermal bypass or the thermal bridge. In the middle, you can insulate it over the top, and that's fine, but it does create a lot of work and a lot of surface area for the heat to escape in, and you're heating up that parapet. On the last one here on the right, this is a detail we've seen used down in New York City on some schools where the roof insulation is in plane with the thermal break that's right under that concrete parapet, and it's permanent and it's long lasting and it's in plane so that you have the continuity and the insulation that you're looking for. There's a lot of different ways to build parapets. I'm not going to pretend to how to design this, but we really have to. This is an area right here that's very important to get right. Weight bearing, where your roof and your wall are connected. Roof penetrations, you could probably imagine there's a lot of them. In this case, fall protection. There are ways to attack that. You just have to get the thermal breakup in plane with the roof. And if you don't, you might get condensation. And that's true of a lot of these details. And just because I find it's interesting, people don't really understand relative humidity is the air's ability to hold water vapor relative to the temperature. And in the built environment, if you have 70 degrees in your room, and somewhere along the line, 70 degrees is able to hold a lot more moisture than 50 degrees. And if you do have like 55 degrees somewhere in that building, you're going to get condensation, or you may get condensation depending on how much humidity is in the air. We see this a lot in steel buildings. When it happens, hopefully it's not in a place that is hard to get to, but they always are, and they could cause rust, rot, and corrosion. Mold also loves that moisture, and mold can be a problem in those type of situations because they're just sitting around waiting for the water necessary to help them bloom. And when they do, it can be a major problem, whether it's an insulation omission or poor circulation, like as you might see here. But we know across the top here, this is a thermal bridge because it's a steel beam holding the steel beam in that header there that goes across that window detail. So we can go at it this way, or we could reduce the cold spots that could be thermal bridging. Code is here. I don't have to tell you, in Massachusetts, we're full on with the stretch codes and so forth, but that's not true. Sally and I do these all over the country, and some places they don't know what we're talking about. So it's same thing is true in Canada, by the way. And so the ASHRAE standards, and especially on the demand side, are going in one direction. We're making more strict, more stringent details about how to control how much we use on the heating and air conditioning side, and thermal bridging is emerging as one of those areas that we really need to improve. The US GBC and the Canadian folks that do the same thing are on board with V5. Thermal bridging is a major component of that. There are some tax credits left. You could look at Desire, www.desireusa.org to find if there's any tax credits in your area. But net zero carbon buildings are within our reach. Passive house and all the others thermal bridging is a big part of the strategies to stop the waste in those areas. That's it for the main part of this presentation. Thank you for that. Let me just tell you a little bit about Armatherm. And so our three product lines are I mentioned at the beginning, Armatherm FRR, fabric reinforced resin. It's a phenolic resin, very, very strong. It's reinforced with fiber, and it creates a pad in most cases, a pad, often used to connect steel together. And this pad is, as I said, very strong, 43,000 pounds per square inch of compressive load. It can be, we cut this on a CNC machine, and it makes uh, all kinds of cool designs. If you needed that and you at a beam or whatever, we have washers and bushings. I have a slide on that in just a second, but this can be done in many different thicknesses. We can bond it together and deliver it 1 inch, 2 inch, and everything in between. These specifications can be found on our website. So you can see 43,000 pounds of compressive load, and standard thickness is 1/2 inch, 3/4, 1 and 2. But we also have shims that can make it add a 16th or an eighth or whatever it is that you'd like. This talks about the washers and bushings, and this is also on our website to add a little bit of insulation on the bolts. F500 series is this series of the series of ultra high density polyurethane. This guy's our strongest, but has an R value of just under 2. And this is our also strong, but not as strong. And that is our is much better R value. But they're available in different densities because there's different applications. And you'll see this also, you can find this out there. You can see here that our 080 material is it's still very strong, 210 pounds per square inch, but it goes up to 2150, which is 10 times as strong, and about half the R value. But passive house folks are coming to us all the time with different applications for these. This just shows that we trade off is the trade-off is strength for R value. So finally, our pultruded fiberglass Zegerts come in 7 in-stock sizes from 1.5 to 6 inches. We have tons of in-stock ready to ship, which is something that we are pretty proud of. We keep high stock levels. This again, the specs can be found on our website, and these are the 7 sizes over here, and they would naturally be for different thicknesses of insulation, different types of insulation. And finally, the RJC doesn't sound like much, but if you're an installer, these little clippy things here that are used to hold the insulation in place while you go to lunch and you come back and the insulation's still on the building, that just holds the insulation in place before the cladding goes on. So that's it, folks. I know you're sorry to hear that's the end of it. We're pretty far along here. And if there's any questions, we'd be happy to try to answer them now or later.